recognize covalent bond type. If we look at our periodic table, draw its shape here real quick. Our staircase is the dividing line between our metals and our nonmetals. If you're below the stairs, you've got 1 dot, or you've got 2 dots, or you've got 3 dots. And then on the stairs, generally, you'll have 4 dots. If you're above the stairs, you may have 5 dots. And at this point, we start filling up pairs of electrons. And so you may have 6 dots with 2 pairs that have filled up, or 7 dots with 3 pairs that have filled up. So how do you know if a compound, if a substance you're given is going to be covalent? Well, you look at the first element and it's not a metal. So covalent bonding occurs when the nonmetal with a lot of dots reacts with another nonmetal with a lot of dots. So for example, if I gave you 3 random substances, one is NaI, another one is, let's say it's MgO, and I get a third one that is NCl3. I look at the first element. Sodium is way over here, and it has 1 dot. Magnesium is over here, and it has 2 dots. But nitrogen is over here, and it's got 5 dots and a lone pair. Like that. These are both metals. They're automatically going to form a plus and a 2 plus. But nitrogen is going to combine with a chlorine that also has electron pairs. And neither of these elements are going to give up electrons. There will be no positive ion or negative ion. They are going to share. And that's how we know that we have a covalent bond. All right? So you've got more dots for both the elements that are coming together. A lot of them have lone pairs that are filling in already. If it's a metal at the beginning, it's always going to form those ions. And whatever it's with will also form an ion. So in this case, the iodine with his 7 dots and 3 pairs that are stable needs an electron, so you'll have a plus and a minus, and this is ionic. The oxygen has 6 dots, and he just needs 2, so he's going to go 2 minus, and he's ionic. But these guys are not going to form ions. They're going to take the open spots, and they're going to need to create bonds. So when you have nonmetals, you could have a nonmetal that has 4 dots that's found in column 14. Carbon is a really good example. You could have a substance that has 5 dots, like nitrogen, or 6 dots, like oxygen, like this. Or you could have something that has, like chlorine, something that has 7 dots. That looks terrible. Cl. With 3 lone pairs and a single dot. And all 4 of these are going to make bonds by sharing. Okay? So we notice that if there are 4 dots, you need to make 4 bonds. And there's a number of ways to do it. This element could bond with 4 single connections. He could connect to 4 different elements as he fills those empty spots. he could connect twice in a double bond to one element and to two other bonds, to two other elements with single bonds. So he could connect to 3 atoms. He could also connect to 2 using 2 double bonds, but he can't connect. He could also connect to one with a triple bond and a single bond, but he's not going to be able to connect to just one atom with 4 bonds because the electrons have to stay. Some electrons have to stay on the other side. So you have these 4 different possibilities as the 4-dot element starts making structures. If there's 5, if we think of its possibilities, he could go with 3 single bonds to 3 elements. He could go with a double bond and a single bond, keeping his lone pair, to 2 elements, or he could just simply triple bond to 1. So I've got 3 options. You can connect to 3 atoms, to 2 atoms, or to 1 atom. All these different possibilities make the world so incredibly diverse, as each type of bonding, each structure, each combination makes a new molecule that has new properties. So if I go with, if I have 2 lone pairs, I could bond to 2 atoms, or I could just bond to 1. But there's not many options for 3 lone pairs. They're always just going to make a single bond. And the other element that's like the halogen, which is found over here in group 17, like fluorine and chlorine and bromine, these guys make single bonds. The other one that makes a single bond, who is also nonmetal, is kind of off on his own, is hydrogen. And hydrogen does not have any lone pairs. He just has a bond. And that's it, because he only needs to fill 2 electrons. Okay, so that's how you recognize bond type. Now, once we've recognized that we're making molecules, it's possible that we could make a polar molecule or a nonpolar molecule. And here's how this works. Again, our periodic table. Boom, boom, boom. There are 3 elements in the uppermost corner, nitrogen, oxygen, and fluorine, where the electronegativity is the highest. And these 3 elements all have lots of pairs of electrons on them. And when you have a pair of electrons that's not bonded, it tends to be negative. Nitrogen has 1, oxygen has 2, fluorine has 3, and their atomic makeup is such that they pull really hard on negatively charged electrons. So, what does it mean to have polar and nonpolar? Imagine I just had a round balloon like this, and it was perfectly shaped. There was no difference on one side or the other. And then imagine I had a magnet, a rod magnet, that had a positive side and a negative side. There is no magnetic force on this nonpolar structure. But on this polar structure, I have a positive side with a magnetic attraction to negative, and I have a negative side with a magnetic attraction to positive. I create the negative pole and the positive pole on this magnet, and by having those opposite sides with opposite charges, that's what it means to be polar. All right? So, if we look across the top of our periodic table right here, in the nonmetal region, okay, we've got carbon, and then there's nitrogen, oxygen, and fluorine. Carbon has a 2.5 electronegativity. Nitrogen has 3.0, oxygen is 3.5, and fluorine is 4.0. Our electronegativity scale goes from a max of 4.0 down to a minimum of 0, and right in the middle is 2.0. The harder our electronegativity poles, the stronger, the closer we get to 4.0, the more likely it is that we're going to get some negative. The farther we are, the closer we are to oxygen, the more likely we're going to, or not to oxygen, to 0, the more likely we're going to have a positive. So this region up here, between 3.0 and 4.0, these guys almost always go negative. In this region, they're more neutral in how they pull. So, for example, let's bond nitrogen to hydrogen. Nitrogen's a 3.0, strong. Hydrogen's a 2.1. The electrons that are found in the shared bond here in the middle are attracted more to the electronegative nitrogen than they are to the hydrogen. So this structure with two atoms sharing electron clouds like this ends up with partially negative electron cloud over here and a partially positive electron cloud over here. And that right there is polar. All right. You'll also notice nitrogen will always have a pair of electrons that aren't bonded to anything. And that lone pair of electrons will always have a slightly negative charge as well. So we get a structure when these two atoms are bonded together that is polar. And it happens with nitrogen with his one lone pair, oxygen with his two lone pairs, and fluorine with his three lone pairs. Those are our structures that when they're bonded to hydrogen, they create polar molecules. Carbon over here, if carbon was bonded to hydrogen, it's only a 2.5 and a 2.1, and that difference, they pull pretty much the same to the point where there is no shift. There is no creation of polarity. It's just neutral. All right? So how do you recognize bond type, whether it's polar or nonpolar? Let's look at a couple. Let's say we have CH4, NH3, H2O, or HF. Those three guys pull. Those three guys have strong electronegativities. So these three molecules are going to be partially negative, partially positive. Partially positive on the H, partially negative on the O, partially negative, partially positive. All I need to see to know that it's polar is an N, an O, or an F. That's the easiest way to tell. This CH4, there is no polarity. Okay? So, CH, none. NH, OH, and FH, they're polar. And that's how you recognize the bond type, whether it's polar or nonpolar. All right? All right. Now, how do I go from recognizing the bond type to drawing the structure? Well, let's look at a couple. Let's say we have a molecule that is CH3NH2. Okay? First of all, is it polar or nonpolar? There's the N. That N is going to be partially negative, which means the H has to be partially positive. So yes, this molecule is going to be polar. How do I draw it? Carbon always has 4 connections, like this. If I see a CH3, I know that 3 of the connections to carbon are already H's. This structure matches CH3. Now, nitrogen has a pair that doesn't bond. So nitrogen will always need to make 3 bonds. When I see the NH2, the N is bonded to the carbon, and there's a lone pair, and then the other 2 bonds are just the hydrogens. Okay? So, how do I know this is polar? There's a lone pair. That guy's going to be partially negative. I keep drawing this little curvy D, and it's the delta, which means partial negative. So I have delta negative, and opposite, anything that's attached to the nitrogen is going to become partially positive as the nitrogen pulls the electrons that direction. This one might be slightly partially positive. But we remember that he was only a 2.1, but his strength is a 2.5, so it's more likely the electrons are coming from the hydrogens. So, I have a polar molecule. Let's look at another one. Let's look at C3H8. All right, I know that carbon needs to make 4 bonds, and I know that hydrogen can only make 1 bond. So as I draw this structure, I'm going to connect 3 carbons together like this. And each carbon needs to make 4 bonds, so I can attach 3 more bonds onto the outer carbons and 2 onto the inner. And so I get H's, there should be 8 of them, attached all the way around like that. Now, do I see an N, an O, or an F? No, I don't. So all of the electrons in the electrons clouds that make up this connected molecule, they're even, and this is nonpolar. There's no partial charges. Let's try another one. Let's do C2H5 2NH. All right, tricky. So when I see a parentheses in the structure, what it's telling me is that whatever's inside, I have 2 of them attached to this. So what is C2H5? Let's take 2 carbons and bond them to each other like that. In order for me to fill out the rest of the bonds on the first carbon, it requires a CH3. To fill out the bonds on the second carbon, it requires 2 more. And then there's a bond here that can be connected to anything it needs to connect to. So C2H5 is this. And there's 2 of them. And they're attached to the N. So I have an N right here that has a lone pair like that. And it has another 2 carbons and 5 hydrogens attached to it. And there's an H right there. So if I see this, I have C2H5 and C2H5. There's 2 of them attached to a nitrogen with a lone pair because the nitrogen has 5 dots. And then there's a hydrogen attached here, and that's what this guy is. Is this polar? Well, yeah, I have a lone pair. That's partially negative. Nitrogen is also a strong pull. So he's going to be partially negative. And this hydrogen, not these, but this one is going to be partially positive. Because this one's hooked to a nitrogen, those are hooked to carbons. The rest of this molecule, this region here and this region here, is going to be nonpolar. But these guys right here in the middle, that creates a pole. I've got a negative side and a positive side. There's my polar region. Okay, so we're starting to see that sometimes molecules, as they get more complex, can have chunks that are nonpolar and can have chunks that are polar. And other molecules that are polar or nonpolar can then start interacting with them. So that's how we would tend to draw the structures. Okay, so how do I know what their properties are? Okay, let's draw a line down the middle of our page here. And let's say this is polar and this is nonpolar. Okay, let's say I have a small molecule. It's got two atoms bound together like this, maybe an H and an F, and it's polar, so this side's partially negative and that side's partially positive. At the same time, let's say I have a small atom over here, and this one, or a small molecule, there's two atoms, over here, and it is nonpolar. There is no partial positive and partial negative. In order to recognize the properties, you have to ask yourself a question like, what if I had 1,000,000 of these, and they were all interacting with each other, flying around? Well, when I had 1,000,000 of the ionic crystal building blocks, and those were all interacting with each other and all sticking to each other, they created a locked crystal. And the reason they did is because this charge is so much stronger than the partial charges that might be here. So if I had 1,000,000,000,000 of these molecules and they all interacted with each other, these molecules would stick and probably slide. So can you imagine all of these structures stuck to each other, but they're flowing and they're wiggling and they're moving, but they can't quite escape touching each other because the partial charges are holding them together. So when you have a small polar molecule, you tend to get a liquid. Okay? Imagine you had 1,000,000 of these small chargeless molecules, nonpolar molecules. They could maybe sit on top of each other and fill up the bottom of a cup if there was no energy involved. But as soon as these guys start wiggling around and they start wanting to fly around, there's no attractive force that's going to hold two of these guys together. These guys become a gas. Okay, so for example, H2O, when we look at H2O's structure, the O has two lone pairs, and there's our partial negative, right? Partial negative. And then the H's end up being the partial positive. And look what we have here. We have this small molecule that's partial negative on one side, partial positive on the other. And this water molecule tends to be a liquid because the partial charges hold it together but don't lock it in place. Unless we take so much energy out of the molecules that they're not moving as much, and then they crystallize into an ice cube, right? If I energize the molecule enough to where it can overcome the attractive forces, then it'll turn into a gas. But you have to get it all the way up to 100 degrees Celsius to do that. Now, over here, what if I had CH4? I have a carbon with 4 hydrogens around it. And I'm drawing this structure so it looks three-dimensional. You can see that this one's coming out at me and that one's going behind. And this one's in the page and that one's in the page. So I have this. It sits flat like this, and then there's another one that's angled like that. So it's got a three-dimensional shape. But that three-dimensional shape is balanced and not charged. So if I had 1,000,000,000 of these all interacting with each other, CH4 tends to be a gas. Okay? So nonpolar tends to be a gas. Polar tends to be a liquid. But what happens if I start adding more and more H2Os? Or excuse me. What if I start making the molecule a little bigger? What if it's medium sized? So what we're going to do is, if we take this water molecule like this, that's our perfect polar structure, O stuck to H. If I remove one of the H's here, I can then attach it to anything I want to attach it to, okay? So what if I took this OH and I attached it to a chain that had 3 carbons, like this. And I put an OH over here, like this. And I put an OH on this side, like this. And I put an OH on this side, like that. I'm just making up a molecule right now. And then let's say I just had an H there, and I just had an H there, and I just had an H there, and I just had an H there. Let's double check. Our carbon has all 4 bonds. Our oxygen has 2. This oxygen has 2, and this oxygen has 2. This carbon has all 4, and this oxygen has 2. Now, look at this structure. I've got my polar connected, looks like water, positive and negative piece. I got a negative over here and a positive over here, like this. I got a negative over here, partial negative, and a partial positive. The way that I'm recognizing those partial negatives is just wherever the lone pair is, and then the oxygen that's attached to hydrogen. And so there's another one here, partial negative, or excuse me, partial positive and partial negative. Now, imagine I had 1,000,000 of these molecules. So it's bigger. It's bigger. It's got more electron clouds. It's got more pieces, right? But if I had 1,000,000 of these, another molecule might come next to it. And if he just flips over, boom, the H's align with the O's and the O's align with the H's, and we just lock in place, don't we? Or another one could come over here and lock in place. With all of those polar pieces, each individual molecule can lock in more than one position, and it's harder to slide around. So as we get bigger with more and more polar pieces, we start to turn into a solid. That might be a crystal. But we're only held together with partial charges. It's not like our ionic plus stuck to negative. These guys lock together in a strong crystal. These guys are kind of locking together, but they melt easily. They'll go back to a liquid with a little energy added. It's not as strong a crystal as when it's ionic. But what happens if I get a medium-sized carbon chain? What if I make C3H8 with 3 carbons? Or what if I make C4H10 with 4 carbons? Or what if I make C8H18 with 8 carbons? I'm making these nonpolar molecules much bigger. So if you can imagine I've drawn all the H's on here, right? They've all got H's on them. It's just filled up all the way around like this. So I get this molecule of 3 atoms with H's all around it. And I've extended the length of the molecule by 1 carbon here, and I've doubled the length of the molecule here. And it's just a nonpolar big carbon hydrogen cloud, all held together. Okay. If I have a balloon that's nonpolar, and I have my head that generally doesn't have a charge, it's just my hair and it's my gorgeous face and stuff. Sometimes when big nonpolar structures come in contact with other big nonpolar structures, they can rub back and forth. They can move each other. And what tends to happen is you get a little bit of the shift, a little bit of shift of the negative closer to the surface here, and a little bit of shift so that it's positive closer to the surface here. And then with a really, really weak attractive force, that balloon will stick to my head, right? So if I had a million of these, or a million of those, or a million of these, as I've extended the length of the molecule, I can now have a second molecule that can actually rub up against it with a little bit of surface area. And if it's possible to get that rub or that connection, we'll get some partial positive and partial negative that'll stick. And this is called a dispersion force. Okay? So nonpolar on nonpolar is like rubbing a balloon on your head, and they'll stick a little bit. But it's not near as connected as a dipole to a dipole. That's why this ended up being water, and that didn't have near enough attraction to be a gas. A little tiny molecule doesn't have any surface area. Two of those guys against each other don't have any surface area they can stick. But as I make it bigger, they start to stick a little bit. Now watch what happens here. This is methane gas. And it's really hard to turn that into a liquid. It has to get crazy cold. They don't attract each other because there's so little surface area where you can have these dispersion forces. As I increase the length of the carbon chain, now I've made propane gas. This is propane. But this propane, all you have to do is pressurize it in a propane tank, and it turns into a liquid because the molecules are a little bigger and they can actually attract each other a little bit. If I add another carbon, this is butane, which is the liquid fuel that they put into lighters. So by extending the surface area where these molecules, a million of these molecules all together, interacting and rubbing against each other, they could start to stick. Not very well. Butane evaporates really easily. Like the molecules can escape that attractive force and evaporate pretty easily. But this one down here is octane, which is one of the main ingredients for gasoline. And this one's 8 sections long. So it's fairly easy to rub against. If I had a million octane molecules all rubbing against each other, they would make a liquid. So when you have a medium-sized nonpolar, you get these liquids that stay together, but they stink because they're evaporating so easily, and you can smell them. They're very volatile. So the medium-sized nonpolar tends to be really, really volatile liquids. All right. So what if I make my molecule huge, really big? Something like C12H22O11. This is sucrose, which is sugar, table sugar, right? If I took 12 carbons, carbon, 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 there's 6 in a ring, and I made another ring just like it with the carbons. I'm really just shorthanding these structures because I'm drawing the parts that are most important, but anywhere there's a carbon that's missing a bond, we've got a hydrogen attached to it. But if you'll notice here, I have 11 oxygens. So each one of those oxygens creates one of my water-like polar, partial negative, partial positive pieces. And I'm going to put these all over the place on every carbon, right? We've got OHs everywhere. And every single one becomes this little attractive polar magnetic, not magnetic, but electromagnetically charged, so that I have a partial negative with a partial positive. And this is a huge molecule. I've got all these OH is everywhere. There's another one here and another one here. I don't know if I did that right. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I have all of those oxygen, hydrogen groups with the partial negative on the O and the partial positive on the H. And the rest are filled in with hydrogens. So I've got, this is a sugar molecule, this big ginormous thing right here like this, big old sugar molecule. If I had 1 million of these, would they interact with each other in a way that they would lock in place? If I took a second molecule and I flipped it so all the O's attached to the H's and the H's attached to the O's and let these guys just like lock in place, I'm going to create a crystal. And this crystal is what we see when we've got sugar. Is this crystal of sugar, is it going to have the same properties as salt? No, of course not. Salt has a stronger bonded crystal. Salt is not going to melt, but sugar melts beautifully with some butter into caramel, right? It gets this brownish color when you try to melt sugar. And the reason it melts is because its crystalline structure, it's locked together, is not locked together so strongly that it can't start sliding. All right. This structure, if there's only 4 OH regions, it may crystallize. It may form a crystal, or it may just be a thick liquid. But this one's definitely going to melt before this one, because the larger the molecule, the more attractive force, the less it's going to go. All right. What if I had a big, huge hydrocarbon? Okay. What if I had like C50, H1O2, right? So I have a carbon attached to a carbon, 3, 4, 5, 6, 7, 4, 5. Oh no, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. Don't quote me, but that's kind of 50 carbons all linked together like this, right? This was octane, 1, 2, 3, 4, 5, 6, 7, 8. That length, that much surface area made a liquid. Can you imagine having this much surface area? I'm essentially making a piece of spaghetti that's not attractive to anything else, but if it rubs against something, it'll stick a little bit. I'm making a big piece of spaghetti. And if I have 1 million of these big pieces of spaghetti and they all interact with each other and wrap around each other and do all of this kind of fun stuff, they're going to hold in place. They're going to hold in place and make a solid. But that solid is going to be waxy or buttery, squishy, greasy. And that's what we see from nonpolar big molecules. All right. So really fast. How do I recognize covalent bonding? Non-metal with non-metal. They're the elements that have lots of dots and lone pairs. And if you put them together, you have to make molecules. And there's so much versatility. If there's 4 dots, you can bond 4 different ways. You can bond 3 different ways if you have 3. So there's all these different molecular connections you can make. It's 2 elements above the stairs together. And the easiest way to know it's covalent is just to check. Is the first guy a metal? If it is, you're dealing with ions. If it's not, we got to build the molecules and figure out then if it's polar or nonpolar. And how do I recognize if it's polar or nonpolar? When it's polar, one side gets pulled to negative, one side gets pulled to positive, and you create a dipole. And the guys that create dipoles are N, O, and F. Those guys right here. How do I know if it's nonpolar? Carbon. Carbon tends not to form polar regions. There's no imbalance of negative and positive. So How do I draw the structures? Well, hydrogens can't be in the middle. So we'll take a look at the structure and we'll just piece together the bonds until they connect in a way that everyone has the bonds they need. So we put our carbon, 4 bonds. The CH3 tells me I've got 3 bonds bonded to something, which is the nitrogen. And the reason I only had 2 hydrogens on the nitrogen is because he has that lone pair. C3, that's 3 connected carbons, and then we fill in all the hydrogens. This one was tricky, but I had 2 carbons creating a section that had 5 hydrogens. So C2H5 could then bond to something else. And if I have parentheses with a 2 outside, that means I have 2 of those structures. Boom and boom, right there. And then the NH is what's connected in the middle, like that. So drawing our structures is a matter of connecting the dots. But you can get, with practice, you can start to see the parts that are the same every time. Like CH3 shows up here and here. There's a CH3 here. This CH3 turned into C2H5 just by adding another segment. And you'll notice that the carbons love to make chains, just long chains of stuff. Now, what are their properties going to be? Small and polar, get a liquid. Medium-sized and polar, you get a thick liquid, or you get a melty solid. And then really big polar, you're going to get things like sugar crystals. If it's nonpolar and it's small, it's definitely a gas. As you extend the chain of carbon, when you reach 4 carbons, it turns into a very volatile liquid that smells really bad. You get up to 8 carbons in the chain. They'll stick together enough to make gasoline. And then you get really big hydrocarbons, form solids that are really fun, like wax and butter and greases and fats and all that kind of fun stuff. And that's our last. That's it right there. Okay.